Hello, Dr. Vels here. In this video I will attempt to explain what an end-fed half wave is, or EFHW. The basic description of this antenna is that it is a length of wire, usually mounted horizontally in an inverted L configuration, an inverted V, or any other abstract shape. Unlike a dipole, it is fed from one end. The wire is half a wavelength at the lowest frequency of operation. This antenna is a multiband antenna and can be used on harmonically related bands. But how do we match the wire to 50 ohm coaxial cable to be connected to modern radios? We use a 49:1 transformer. Some experimenters have used a 64:1 transformer, but this transforms the rather high impedance at the end of the wire to roughly 50 ohms for compatibility with common coaxial cables and common radio antenna socket impedances. A counterpoise wire is also used. This does not have to be very long. Some people, including myself, have opted to do without the separate counterpoise wire, and we have fitted a common mode choke to the coaxial cable instead. This means that the outer surface of the coaxial cable braid becomes the counterpoise and makes for a tidier installation. The choke is positioned less than a quarter of a wavelength at the highest frequency of operation from the transformer connection on the end of the coax. That is shown as X on the diagram. This rule also applies if you use a separate counterpoise wire. It is often recommended that a 100 picofarad capacitor is connected across point Z on the diagram, which improves matching on the higher HF bands. This capacitor has to be of a high working voltage. Many recommend a voltage of 1000 volts. Mine is around 630 volts, I do believe. When we look at how to calculate the length of the wire, we take our lowest frequency of operation, which can be determined by what we wish to achieve on the radio and can be governed by the size of the area in which we have available to us to install the wire. For my situation, I opted to use a lowest frequency band of 7 MHz, the centre of which in the United Kingdom is 7.1 MHz. So to make a rough calculation, we divide 300 by 7.1 to make just over 42.25. Divide that by 2. That gives us the half wavelength in meters, and in this case the wire length is 21.127 meters approximately. This will have to be adjusted due to the velocity factor of the wire used and other environmental factors which can alter the required wire length. But that can be easily adjusted once installed if a little thought is given to the installation. As an experiment, I decided to select the 50 MHz band as the highest band of operation. So I chose to calculate the counterpoise length by using the frequency of 52 MHz. So we divide 300 by 52, which makes approximately 5.769 meters. That is the approximate wavelength of 52 MHz. So we find a quarter of that by dividing by 4. We see that the counterpoise length, or in my case the distance from the transformer end of the coaxial cable and the common mode choke, must be less than 1.442 meters. So I have used 1.2 meters. The common mode choke is simply 8 turns of the coaxial cable wound on an FT240-43 toroidal core. Here we have the theoretical radiation plots of a 7 MHz end-fed half wave wire that's mounted horizontally at 10 meters above the ground. Theoretically, at 7 MHz, the radiation pattern is omnidirectional. But 14 MHz, there are 2 lobes. 21 MHz, we have more of a 6-lobe pattern. And 28 MHz, even more lobes. We have 8 significant lobes there. On the unrelated bands, 10.1 MHz is a strange, almost omnidirectional pattern. 18.1 MHz is a very obscure pattern, and 24.9 MHz is strange as well. So these theoretical patterns give us an idea of how the antenna should perform. Height above ground and other environmental factors will alter the radiation pattern, but this gives us some idea as to what to expect. A certain amount of tuning using a pi match or some other matching circuit will be required on the 10.1, 18.1 and 24.9 MHz bands. On the 7, 14, 21 and 28 MHz bands, tuning may not be required at all, so that makes this quite a versatile antenna and fairly useful for portable operation. Here is a list of the frequencies at which the 7.1 MHz end-fed half wave should be resonant. We have the fundamental frequency at 7.1 MHz, which sits nicely in the centre of the UK 40 metre band. Next we have the second harmonic at 14.2 MHz at around the centre of 20 metre band. The third harmonic at 21.3 MHz is just a bit higher than the centre of the 15 metre band, and the fourth harmonic sits around the centre of activity on the 10 metre band at 28.4 MHz. Because I mentioned the 50 to 52 MHz band earlier, the 6 metre band, I have included the 7th harmonic at 49.7, which is fairly close to the 6 metre band, but I do not know how well the antenna would perform at that frequency. Many people install an end-fed half wave that is resonant at around 3.5 MHz. And if you have the space for this kind of aerial, then that is a very nice thing to try, because when we look at the list of resonant frequencies, we have obviously 3.5 MHz at the fundamental in the 80 metre band, the second harmonic at 7 MHz in the 40 metre band, the third harmonic at 10.5 MHz, which is close to the 30 metre band. The fourth harmonic is within the 20 metre band. The fifth harmonic is close to the 17 metre band at 17.5 MHz. The sixth is in the 50 metre band. The seventh is close to the 12 metre band at 24.5 MHz. The eighth harmonic is in the 10 metre band at 28 MHz. And just to include the 6 metre band, the 14th harmonic sits at 49.0 MHz. Not sure how well that would perform, but again that is open to the experimenters. Well, I hope you found that interesting as a theoretical overview of the end-fed half-wave antenna, which has become very popular in recent years. Thanks for watching, and hopefully I'll see you in the next video.